Hello, hello.
Hello.
How did your midterm go for 118B?
Low-key not bad for the
That's
first one.
good. Yeah. I heard the average was like 60%, like around 60% for both sections.
Yeah, the average was pretty low.
Yeah. See, but would you say it was pretty similar to the practice exams that Helix gave out and the ones that like uh I gave to you? That's good. Yeah. Okay. Let's see. And you guys have another midterm next week. Oh my gosh, so soon already. Mhm.
Hi, Bryant. How are you?
Doing fine. How are you?
I'm pretty good. I'm trying to grind for OChem so I can save
Mm.
myself the stress for next week.
Yeah, that's good. Next week it's gonna be like on chapter uh like the alkyne chapter and the kinetic thermodynamic chapter. Did he already give out a study list for it
Mm.
and practice missions for it? Yeah.
I'm gonna be honest, I don't really know. I
Mm-hmm.
know I've just been looking over the lectures and he's been kind of pointing out or he's been going over alkynes. I don't know if he's
Alkynes.
finished yet, but we finished I think the last couple things that we did was the involvement of radicals in alkynes,
Mm.
like
Right.
moving a single radical and
Mm-hmm.
stuff like that.
Yes, radical. So a lot of the alkyne reactions are very similar to the alkene reactions. I created
Yeah.
practice problems here with alkyne reactions that you need to know here. So there's like 16 of them. We could go over these, or if you guys have any questions, we could go over that first. Um, do you guys have any questions before we start on this practice worksheet here?
I don't think I have any questions on my
Mm-hmm.
end.
Mm-hmm. Okay. What about Layla, Peyton, Wiley?
Honestly, I'm like
Nah.
so lost right now, so I'm down to go through this first and then see.
Okay, yeah. Let's do go down this list and see. This is gonna be in the order of the reactions that you learn as well. So, yep, these are just reactions and mechanisms. These are not like nomenclature. Yeah, I'm not gonna talk about the properties of it, which will be important later, but I'll explain that as we go through these problems here. Okay, so let's do it one by one. Oh yeah, I didn't have office hours yesterday or on Monday because I had like so much exams going on this week. So I was pretty overwhelmed. I had to cancel yesterday and Monday, but um, no, I passed all of them so far. I have another one on Friday, so that's pretty good. Yeah. Uh-huh. So for the first reaction here, we have this alkene in a two-step predicted product problem, right? If you see two steps like that, just focus on one reaction at a time and ignore the other steps. So just look at the first set of reagents and what that would do to this reactant molecule here, right? And what I like to do for these predicted product problems is I like to see what functional group is present in the reactant molecule. And the most important functional group we see here is that alkene. So now I start thinking about the alkene reactivity and what they could do, right? Because a lot of these reactants and organic molecules will have different functional groups, and those functional groups have predictable properties, predictable reactions, and that's like why you're learning about these reactions one functional group at a time. Back in 118A, it was about like haloalkanes and their SN2, SN1, E1, E2 reactions, and then you started learning about alcohol reactions and then ether reactions. At the beginning of 118B, we started learning about alkene reactions, and then we move on to alkyne reactions. So you notice that as you progress through OChem, you learn the reactions mechanisms like one functional group at a time, right? But then you get to connect them back to previous reactions you learned. So thinking about this, what would this alkene do with that Br2Cl CCl4? Yes, it would make a vicinal dihalide, which are gonna have two halogens adjacent to each other, vicinal to each other. And what would be the stereoselectivity of this reaction? Would it be Anti-addition or syn addition? Anti-addition. Yes, that's correct. There's no regioselectivity. There's no Markovnikov or anti-Markovnikov addition because both carbons here are equally substituted. But even if one carbon is more substituted like that, we can't say anti-Markovnikov or Markovnikov because we're adding the same thing on both carbons, bromine, right? But if this CCl4 was, let's say, water or alcohol, ROH, then what would be the regioselectivity of that reaction? Would it be Markovnikov or anti-Markovnikov if the solvent was protic instead of aprotic? Where would the water or alcohol attack? Would it attack the more sub carbon of the bromonium ion, or would it attack the less sub carbon of the bromonium ion? So in this reaction here, think of it as like epoxide ring opening in acidic conditions. Because in acidic conditions, we have this three-membered ring with the positive charge right there. And when you have a positive charge right there, think of that as a good leaving group. And there's two ways that we could break off this good leaving group, right? We could break it off at the more sub position, creating a positive charge here, or we could break it off in the less sub position, creating a positive charge here, right? So there's going to be a bigger positive charge on the more sub position because that's more stable position, right? More hyperconjugation. So that's why the more sub position is more attractive for these protic solvents here. So these would attack the more sub position, inverting the stoichiochemistry, right? But that's if we have a protic solvent. In this case, we don't have to worry about that. Doesn't matter. We have a protic solvent. Okay, so let's just put bromine, wedge, dash like that. Doesn't matter which one. It could have been either way. That's the product for the first reaction. Let's move on to the second reaction. Whenever you guys see Na, what charge is that associated with? Positive charge, right? That means that whatever is attached to it is going to be negatively charged. So the negative charge here is NH2 minus. And this NH2 minus here is a strong base, right? It's specifically a small one, not bulky one, right? Because there's only two bulky ones that you guys need to know, LDA and terbutoxide. So this is a small, strong base. When we have a small, strong base and secondary alcohols, do you guys remember what kind of reaction that would be? Like, it's one of the SN2, SN1, E1, E2 reactions. What reaction would we have if we have a secondary haloalkane with a small, strong base? So SN2 would be if we had a primary haloalkane, something like this, right? We have a haloalkane, and this substrate here is primary, where it's only attached to one other carbon. Then that would be more SN2. But because we have a secondary haloalkane with a strong base, then we want to do E2 reaction, which creates an alkene. Yep. So, yeah, it's okay. It's okay. So this right here would do an elimination reaction, E2 reaction. And like Wiley said, it would be a double elimination 2 times because we have 2 equivalent of the strong base and 2 good leaving groups right there. So if I were to draw out the mechanism for you, let's do it like this here. Okay, so I'm just gonna put the bromines as flat lines because we know that it could have been both ways, right? And I'm gonna draw out one of the hydrogens right there. This strong base here is gonna grab that hydrogen, make a double bond right there, and kick off that good leaving group. So those 3 arrows happen simultaneously at the same time, where the first arrow here, well, since all these happen simultaneously, I don't think of it like happening all at once. The way that I logically think about it is that as this strong base here approaches this hydrogen, the bond between that hydrogen being grabbed and that carbon right there goes to make a double bond right there between the hydrogen carbon and the substrate carbon. But to conserve the octet rule, we have to kick out that good leaving group, right? But they technically happen all at the same time. So if you were to draw out like the transition state, you would see dotted lines like that, right? Where these dotted lines mean that bonds are being formed or broken, right? So that's gonna form this alkene right here for E2, right? Where we don't have this bromine anymore. We created this double bond. We don't stop here because we have another hydrogen that we could grab with our second equivalent of NH2 to create another pi bond there to kick off that good leaving group. Now, be careful here. We're adding one more bond to that double bond, which is a triple bond. And do you guys remember the geometry of a triple bond back in Gen Chem or 118A? Like how we would draw alkynes, triple bonds? Uh-huh. Straight, yes. 180-degree bond angle, like that. Right, so do not draw your alkyne like this. Right, that is very cursed. Right, and Levens would not like that. Right, for sure, for Levens. For Helix, I'm not sure. He's more chill. It also depends on the TA as well, like which TA grades your exam. So to keep track, let's see here. 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. Yeah, so that's good. So that is a way that we could form an internal alkyne. This is an internal alkyne. But specifically, it is an asymmetrical internal alkyne, right? Because there's gonna be 3 different types of alkynes that I want you guys to know to do these reactions. There's an asymmetrical internal alkyne, which is this one. There's a symmetrical internal alkyne, where the 2 R groups of the alkyne are equal, where if we have the alkyne right there, inside of the molecule, the 2 R groups are equal. So that would be a symmetrical internal alkyne. And the other type would be a terminal alkyne that I want you guys to know. Right? And the terminal alkyne would be like if the alkyne is by the terminal end of the molecule, something like that. Right? And all terminal alkynes will have a hydrogen on this sp carbon right here. Right? And here's a property thing. This hydrogen there on the sp carbon is acidic. Relatively acidic. Right. So if you use a base like NH2 minus, we could deprotonate this carbon by grabbing this hydrogen. The bond between that hydrogen and carbon being grabbed, those 2 electrons are gonna pop onto that carbon right there, giving that carbon a negative charge, right? And then that can be a nucleophile or a base. Okay, so we're gonna see that, but let's move on to the next one here. Oh, perfect. So, oh no, that's number 5. Just kidding. Let's go number 2. Number 2. We will get there though. Let's see. Copy. Any questions on number 1 before we move on to number 2? So number 1 was just double elimination, double E2 reactions for the second step. First step was halogenation, bromination of the alkene. Because it tells us how many products we end up producing. Yes, that is why this is important. If you have an asymmetrical internal alkyne versus asymmetrical internal alkyne versus the terminal alkyne, that will tell you how many products you end up producing for certain reactions. Right, that is the most important part, why I want you guys to know about these 3 different alkynes here. Okay. Yes.
Can I ask a quick question?
Yeah.
The first one, if we took the other BR away and then it would be positive there, could we have made the double bond like facing towards our substituent group, or would it always have to be like, sorry if this doesn't make any sense. Like if you took away that and then you made the double bond closer to the little group on the dash.
Like this group right here? Yeah, so if we grab this hydrogen right here, and instead of going to like that arrow, let's make this arrow right here, right? We would, let's say, if there was a double bond right there, it would look like this, right? And the bromine would still be here. The other bromine would still be there because we didn't kick that out. But there's a problem here. This carbon also has a hydrogen right there, right? That invisible hydrogen, that's a wedge. If we made a double bond right there, that carbon would break the octet rule.
Okay.
Right. There's no good leaving group to break. And whenever we break the octet rule, we want to kick something out to conserve the octet rule, right? There's no good leaving group at this carbon right there. That's why we don't make a double bond right there, right?
Okay.
We make the double bond towards the side with the leaving group to conserve the octet rule. Yeah.
Thank you.
Of course. Now, you could also say, why didn't we grab this hydrogen over here, right? With that strong base. to make a double bond there and kick out that leaving group. The reason why we don't do that is because we're gonna get this unstable alkyne here. Oh shoot, if that's a double bond, then that should be flat, straight. Right, this is an alkyne, right, which is less stable than this alkyne structure that we can form, right? Because we can technically grab this hydrogen right here, create a double bond there because there is a good leaving group there, but this structure here is less stable than the alkyne structure, alkyne bond, right? Okay, next one, number 2, right here. Okay, what reaction do you guys think is gonna happen between this haloalkane and this set of reagents here? 118A reaction. E2 Hoffman, yes, because we have a secondary substrate, a strong base, but it's a bulky strong base leading to the Hoffman E2, which means that we want to grab the less substituted hydrogen, right? This strong base here does want to grab that more substituted hydrogen to make the more stable alkene and kick out the leaving group, right? But it cannot do that because there's too much steric hindrance going on here, which prevents this bulky base, this big bulky base, from going to grab that preferred more stable hydrogen, right? So its only choice is to grab the less substituted hydrogen, which there's more space there, create a double bond right there, using that bond between the hydrogen being grabbed and carbon. And we're gonna break the octet rule here, right? Because if we create a double bond right there, this carbon here will have 5 bonds. But to conserve the octet rule, that's why we kick off that good leaving group at the same time, right? So those 3 arrows are gonna be the mechanism for E2 creating this alkene here. Okay, now next step, we did that in the last reaction. We chlorinate the alkene, anti-addition. Okay, so this third step here, I want you guys to keep note of this 3 equivalent, right? This is very important for synthesis because if you want to make an terminal alkyne, then you have to put 3 equivalent of strong base or excess amount, right? And I'm going to show you why. The first equivalent is going to grab one of the hydrogens, create that double bond, kick out that leaving group to create this alkene here. Okay. A second equivalent is going to grab that hydrogen, create a pi bond there, kick out that leaving group, and then we get to our desired terminal alkyne product already, right? So this is what our final product would look like, but if this was a mechanism type problem, you don't stop here, right? A lot of students ask why we can't stop here because this is our desired product. Like, why can't we just use 2 equivalent of strong base? The reason why we need a third equivalent is because of lab experimental reasons, right? Like, if we just use 2 equivalents of base here, we don't get this in high yield for synthesis. If we want to get this in high yield, then we have to deprotonate this acidic hydrogen that we talked about earlier. That hydrogen that is on this sp carbon is acidic, so we got to bring in a third equivalent of base to grab that hydrogen and give this carbon here a negative charge. Right. Now, once we have this negative charge, we could just bring in the 4th step, acid workup step, to get back our terminal alkyne, our neutral terminal alkyne. So we basically just got back our terminal alkyne that we had previously right here, right? So on paper, it looks like you just need 2 equivalent to make a terminal alkyne, right? But in real life lab, this wouldn't be formed in high yield. To get high yield, to get 100% of this, then we gotta put it in excess base, a lot of base, to ensure that every single alkyne turns into this alkynyl anion, right? Alkynyl anion, where there's a negative charge on this alkyne right here. And then after we wait for a while, we then put in the acid workup to clean up the reaction and neutralize the alkynyl anion to get our neutral alkyne back. So that's more of a conceptual thing, like why we need 3 equivalent or excess to create this terminal alkyne. Right? Yeah, you could use water instead of H2O plus as an acid workup step. So instead of H3O, you could use water. But if you used water, then you would produce OH minus as a side product, conjugate base, which is not as stable. So not as stable as if you use H2O plus, because if you use H2O plus, water would be your conjugate base, but water would still work, which you might see in predictive product problems practice, right? Terminal alkyne. If you want to synthesize an internal alkyne like this, then you only need 2 equivalent, right? And the reason why is because once you create the internal alkyne, there's no acidic hydrogen, right? There's no hydrogens on the sp carbons there. Those sp carbons have R groups, no hydrogens. Okay. Any questions on number 2?
Wait, could you explain one last time the last step of why it takes the NH or the H?
Yeah. So the last step when we form the terminal alkyne at the beginning, right here, the reason why this H here gets deprotonated is because it is acidic, right? And the reason why it's acidic is because if we were to compare, let's say, this hydrogen's pKa versus this hydrogen's pKa and this hydrogen's pKa, right? Back in 118A, the very first thing that you did to determine which hydrogen is the most acidic is you first draw out the conjugate base, right? So let's say some kind of random base comes along to deprotonate these hydrogens, which would give the carbon that those hydrogens are attached to a negative charge. So if I draw out the conjugate bases of these acids in blue, I get those negative charges. Then once we have the conjugate bases, we then determine what's the most stable conjugate base. What's the most stable negative charge, you could say. And to do that, you could use this acronym called CARIO, right? Where C stands for charge, A stands for atom size, R stands for resonance, I stands for induction, O stands for orbital, right? In this specific case, I'm just gonna tell you guys that we are focused on orbital, aka hybridization, right? Where we could either have sp3, sp2, or sp carbon, right? sp3, there's gonna be 25% s character, sp2 33% s character, sp 50% s character, right? Because for sp3, there's 4 total orbitals hybridizing with each other, but there's 1 s out of the 4 orbitals, 25%. For sp2, 1 out of 3 s, 33%. sp, 1 out of 2 s, 50% s, right? And the more s character something has, the more acidic the hydrogen is, right? And that's because the more s character something is, they are closer to the nucleus, right? That s sphere orbital right there is closer to the nucleus, which in Gen Chem we learned that it is composed of neutrons and protons. So overall, the nucleus charge is a positive charge, right? So that's why this negative charge right here on the sp carbon is the most stable negative charge because it is the closest to the nucleus, right? It's stabilized by that positive charge of the nucleus right there. Opposite charges attract. Negative charge and positive charge attract. Whereas this one here, this sp3 negative charge, is the least stable negative charge because it's the farthest away from the nucleus, right? It has the least amount of s character, 25% s character, 50% s character, right? More s character, closer to the positive charge nucleus, more stable. And if this conjugate base is more stable, then that means that it is less reactive because it's happy, less energy, aka weak conjugate base, right? It doesn't want to react. It's a weak conjugate base, which means that it came from a strong acid, right? And the way that you can think about it is that this is a strong acid because once it gets deprotonated and forms this conjugate base, it doesn't want to go back, right? It's happy as it is right now. Whereas if you think about this weak acid here, once it gets deprotonated, this guy is very angry, right? This guy is very angry. He's not very stable. He's far away from that positive charge. And because he's very angry, he wants to grab his hydrogen back to become what it was before. That's why this is a weak acid, because it doesn't really want to get rid of that hydrogen right there. That's why it's a weak acid, right? If you guys want to think about in pKa terms, pKa of this is around 50, pKa of this is around 44, and the pKa of the alkyne is around 25. Right? The lower the pKa, the more acidic the acid is. Okay. So that's why we want to deprotonate this in lab, because in lab, this is a very acidic hydrogen, right? So we won't get this product in high yield. We want to get that product in high yield, so we got to deprotonate it, get this negative charge. Once we get this negative charge, we then clean it up, make it neutral again by bringing in the acid breakup, H3O plus or water, right? That's why we do it, because of the real life scenario, high yield situation, right? So just remember that, like whenever you get a terminal alkyne, there's this like weird last step that you have to do, unfortunately, for the exam, right? Like you need at least 3 equivalent, at least 3. You could say excess.
Okay, that makes more sense. Thank you.
Yeah, of course. Yeah, that's a common like question too. Like when I was first learning this too, I was like, why can't we just stop here? Like we get our terminal alkyne here, and and that's good, right? But the reason why we don't stop there is because this is not a very high yield. We want to deprotonate everything high yield, 100% preferably to this negative charge, and then once we have this negative charge molecule, we wait for a while, and then we're bringing the acid breakup to get this final neutral alkyne, more high yield. Yeah. Okay. Move on to number 3. Okay, before we move on to 3, 4, and 5, I want to teach you guys the alkynyl anion reactions first, right? So we already know that the terminal alkyne right here has a acidic hydrogen, and the common base that you're gonna see to deprotonate that acidic hydrogen is NaNH2, right? Which basically is this NH2 minus here. So when we deprotonate that carbon and give it a negative charge, we get this negative charge alkynyl anion, which can either be a nucleophile or a base, depending on what reagents you put to it, right? And here in this class, you only need to worry about 3 different scenarios here, 3 different reactions, right? First reaction you're gonna be worried about is a primary halo alkane, which is gonna give you SN2 reaction. Second scenario, secondary halo alkane, which is going to give you an E2 reaction. The third reaction is going to be an epoxide ring opening. So primary halocane, let's give something simple like that. Secondary halocane, let's do something like this, right? And an epoxide, let's do first step, something like that. Second step, something like that. Okay. So let's label this reaction 1, reaction 2, and reaction 3. Let's do reaction 1 first. Once we have this alkynyl anion here, and we're doing SN2 reaction, I'm going to star my nucleophile, which is that negative charge carbon, and I'm going to dot my substrate electrophile, which is that carbon there with this good leaving group attached to it. Right? Because this carbon here is partial positive charge, since it's attached to this electronegative bromine atom, that's partial negative. This starred atom here, my nucleophile, is going to attack that substrate carbon electrophile, and we're going to make a new bond between that star and dot, between the nucleophile and electrophile. When there's a new bond right there, this carbon here is going to have its octet rule broken. So we've got to kick out a good leaving group, which we do have present, which is that bromine right there. Right? And the reason why I star and dot these atoms is to keep track of every single atom, right? So that's the star atom. This is the dot atom. This right here is a new bond between them. And if I were to highlight it in yellow like that, that new bond came from this pair of electrons right here. Right? Those 2 electrons on this pair of electrons are these 2 electrons of that bond right there. Right? That was used to attack that carbon. When it attacked that carbon, it made a bond with that carbon right there. And then this dot carbon here is attached to a CH2, CH3. CH2, CH3. Right? If there's more decorations like isopropyl here, they just put that decoration there, isopropyl there. And that's how you could keep track of where your groups are, atoms are, and avoid adding an extra carbon by accident or removing an extra carbon by accident, which is a common mistake. right? So that's why I star and dot my atoms to keep track of all the atoms, make that new bond there, and everything else is decoration, copy paste. Okay, and that's SN2, right? Nucleophile, electrophile, backside attack, one step. Everything is in one step, SN2. Okay. The second reaction, let's bring in the secondary haloalkane. Think of this as a base now, right? A small, strong base. If I were to label this hydrogen A and then this hydrogen B, which hydrogen would this small, strong base grab to make a, let's say, Zaitsev alkene, more stable alkene, more substituted alkene? Would it be hydrogen A to create this alkene, kick out the leaving group, or would it be grabbing this hydrogen B, create that alkene, and kick out that leaving group right there? Which route? Hydrogen B, that's right. Because that's gonna give us our more substituted alkene, more stable alkene. So grab hydrogen B, create that double bond right there, kick out that leaving group, and create this E2 Zaitsev alkene. And if you want to draw out the alkyne, that's the terminal alkyne right there, where this hydrogen here that I grabbed is this hydrogen B right there. Right. Hydrogen B. Okay. So that's E2 reaction. Now let's bring in the third reaction. So let's bring in that alkynyl anion. This epoxide. So when you see a negative charge on the molecule here, think of basic conditions. We are in basic conditions here, right? And our base here is that carbon with the negative charge right there. And we have an epoxide here. Do you guys remember when we open up epoxides in basic conditions, do we open up the more subside or less subside from 118A? Less subside, yes. Because think of this as SN2-like, strictly SN2-like. We attack the less subside and we also do backside attack. So that's going to be my starred atom. This is my dot atom here. Nucleophile, attack that electrophile. Pop up that ring, break that ring open, like that. And here is where the star and dot technique comes in handy. This is my starred atom. This is my dot atom. This is my new bond right here, which is going to come from that pair of electrons. And now, this is the hard part, right? Just drawing what is attached to that dot carbon. This dot carbon here is no longer attached to that oxygen, right? Because we broke that ring open. We broke this bond and gave it to that oxygen, right? But it is attached to, let's say, this purple carbon right there, right? So I'm going to draw that bond out to this purple carbon. And then that purple carbon is attached to this methyl group, which I'm going to draw out right here. And it's still attached to that oxygen right there. So we didn't really completely kick off the oxygen, but it's floating around in the ether. But it is still attached to that purple carbon right there. But this time with a negative charge, right? Because before it had 2 pairs of electrons, it now has 3 pairs of electrons, right? Because it gained a pair of electrons from this bond right here that broke off. Those 2 electrons went onto the oxygen, giving that oxygen a negative charge, like that. Okay. Now we just clean it up with the acid workup step, H3O+. Make it neutral. Yeah. Final product here with the alcohol. Okay, so the third type of reaction was epoxide ring opening in basic conditions, and our base here is this alkynyl anion, right? You can think of it as Grignard reagent, right? Because in Grignard reagent, we also have that negatively charged bromine ion, which attacks the less sub carbon of the epoxide. So very similar to Grignard reagent, right? It also adds carbon-carbon bonds. This is the new carbon-carbon bond we added right here, but we did not use a Grignard reagent. We used an alkynyl anion with that alkyne right there. So very similar to Grignard, but different reactant. Okay, let's put those into practice by doing number 4, right? Number 3, number 4, number 3. Okay, can someone walk me through this predicted product problem? what was gonna happen in the first reaction. What is going to happen between this terminal alkyne and this first set of reagents? Ignore the second set of reagents for now, right? What will happen between this terminal alkyne at the end and this first set of reagents here? So NH2 minus, right? Because we have a positive charge on the Na, negative charge at the NH2 minus. That's going to be our strong base, which would deprotonate the terminal alkyne, right? Because this is a proton right here, or a hydrogen ion. We're going to deprotonate this alkyne by taking away that proton. So we're going to deprotonate by grabbing that hydrogen and giving that carbon a negative charge, right? So if this was an explanation type of problem, be careful of like the words and that you use, because we're not protonating this, we're not giving it a proton, we're taking away a proton, we're deprotonating, right? Okay. Bases deprotonate, acids protonate. Right. So once we deprotonate that terminal alkyne, we get this alkynyl anion negative charge right there. Okay. Now let's bring in the second set of reagents. What's going to happen between this alkynyl anion and this second reagent here?
Is there a carbocation formed?
No carbocation gets formed because we're not going to do SN1 reaction. We have a primary haloalkane right here, right? And if we go back to the alkyne reactions, when we have a primary haloalkane reaction with an alkynyl anion, then our reaction here is going to be SN2 reaction. SN2 reaction, right? And the SN2 reaction mechanism, no carbocation gets formed. It's only SN1 and E1 reactions that carbocation gets formed when the good leaving group leaves to form that positive charge. The reason why we can't form a carbocation here is because when we kick off that leaving group by itself and we try to create a carbocation right here, this is a primary halo carbocation, which is very unstable. Right? We don't want that primary carbocation. But instead, if this is SN2, we're going to do a backside attack. Attack that electrophile, kick off the leaving group at the same time. No carbocation, right? So if I want to connect them, star that carbon, dot that carbon, connect them. Star, new bond, dot. This dot is attached to a CH2 cyclopentyl group, like that. And that's how you could predict the whole product without adding an extra carbon or losing a carbon by accident, right? So first step, if I were to summarize this, is acid-base reaction. Second step, SN2, right? Where this is the base, this is the acid. Once we move on to the SN2, this is the nucleophile, this is the electrophile, this is the good leaving group. First reaction, acid-base, to produce our nucleophile. Second step, SN2. Okay. Any questions on this one? Okay, let's move on to number 4. Okay, so for this number 4 here, we're gonna deprotonate the terminal alkyne again with a strong base that we have, NH2, but now we have a secondary haloalkane. What reaction would this alkynyl anion do with this secondary haloalkane? Okay. Go back here.
E2?
E2 reaction, yes. So we're gonna grab the most substituted hydrogen, which is this one, create a double bond there, kick out the leaving group to create that reactive alkene and a terminal alkyne hydrogen back, like that. Final answer. Okay, next one, number 5. Right here. Get more space. So number 5, same thing. Let's deprotonate the terminal alkyne hydrogen with the NH2 minus that we have. Give that carbon a negative charge. Now, once we have this alkynyl anion, there's 3 reactions that Helix wants you to know. One with a primary halocane, one with a secondary halocane, and one with epoxide. Right? So we have an epoxide in this case, in the second step. Which carbon are we gonna attack, A or B?
A?
Yay, the less subside, because we're in basic conditions. We have this negative charge right here. We want to attack the less subside, which is this carbon right here. So I'm gonna dot that carbon, star the nucleophile, right? Yeah, we don't attack B because that's the more subside. We are used to attacking the more subside in the alkene reactions because you guys are used to seeing that, right? That's because all the rings that you saw that broke open were positively charged, right? It had like 3 things attached to it, to this random group. And then when we have this positive charge, 3-membered intermediate, that's when we attack the more subposition, right? Because there's a bigger positive charge right there. But in this neutral conditions, neutral epoxide, that's not a good leaving group anymore. So we think of this as strictly SN2, right? We attack the less subside and kick up that ring like that. And let's connect the star and dot. Star, new bond, dot. Dot is attached to green, right? And then this green carbon here is attached to a wedge O minus and this CH2 isopropyl like that. Then we just finish it off by doing acid workup, make it neutral. Like that. Okay. Let's move on to number 6. Have you guys learned about this set of reagents before? These 3 sets? H2PDC, H2 catalyst, sodium in ammonia metal. Okay. Liquid, I mean. Let's see. What would H2PDC do to this asymmetrical internal alkyne? Asymmetrical internal alkyne. I'll give you guys a hint. You guys have seen this reaction in alkenes before too. Right? Like, for example, let's say we had this alkene and we react it with H2PDC. What happens to the alkene when we react this with H2PDC?
Does it add both hydrogens onto the structure?
Yeah, we have 2 hydrogens. We're gonna add 1 hydrogen here, another hydrogen there, get rid of that alkene right there. So we're reducing that alkene into a single bond alkane where we add 2 hydrogens, 1 for each carbon of the alkene, like that, right? So that's hydrogenation. We're gonna do the exact same thing for the alkyne, but we're gonna add 4 hydrogens, right? 2 for each carbon, 2 hydrogens here, 2 hydrogens here, because this is gonna be an excess amount. So we're gonna reduce this alkyne all the way down to an alkane. And the trick that I like to do here is I like to number my molecule to keep track of my atoms. So coming off the ring, we can say this is 1, 2, 3, 4, 5, 6. So let's draw that ring out. Cyclohexane. 1, 2, 3, 4, 5, 6. And at carbon 5, there's a methyl group coming out of there, right there. Right, carbon 5. That methyl group is that methyl group right here. 1, 2, 3, 4. There was a triple bond here, but it's now a single bond. Right, like this triple bond region, 3, 4, is now that alkane right there. Okay. Now, if you want to create an alkene instead, like not an alkane, then there's two sets of reagents you could use. You can use H2 Lindlar's catalyst, or you can use ammonia and sodium metal. Right, H2 Lindlar's catalyst, the poison catalyst one, is gonna stop at the cis alkene. So if we draw out the ring like this, we could create this cis alkene like that. If you use sodium metal in ammonia liquid, then you would stop at the trans alkene. 1, 2, 3, 4, 5, 6. Like that. Trans alkene. Right. And this is very important, especially for synthesis, because sometimes you'll see that you have a cis alkene or trans alkene, and then from that you could do the alkene reactions depending on what you want. And then that's when you have to use, like, choose between H2 Lindlar's catalyst or sodium metal in ammonia liquid. Yeah, so Lindlar is cis because you don't need to know the mechanism for this. This Lindlar's catalyst here is a poisoned catalyst, and that stops at one equivalent. Wait, stop at one equivalent of H2. So you know how when we learned about the alkene reactions, this hydrogenation here is syn addition, meaning that when we put hydrogens on both carbons, here and here, those two hydrogens attach on the same side. So if one hydrogen is a wedge, the other hydrogen would also have to be a wedge. That's syn addition, right? Same as for here. This is also syn addition. One hydrogen is on top of the bond. That means the other hydrogen has to be on top of the bond as well to maintain that syn addition stereochemistry, right? And we stop here. We stop here. We don't add the equivalent of H2 because this Lindlar's catalyst is poisoned, right? It's not going to react again with the alkene. So we slow down the reaction to stop at the cis alkene, right? And the reagents that you see for Lindlar's catalyst, I forgot what they were. It's like PB, like OAC2, something else with like PD, something like that, or like with calcium O3, something like that, CO3. Right.
Was it the like was there PTO2?
Something like that. I think so. I think PTO2.
And like R
Yeah.
like with nickel?
Yeah. I think so. Yeah, R nickel, something like that.
RD and something like that.
Yeah. Right. But in most reactions, I've seen Lindlar's catalyst. But just in case Helix tries to trick you guys, and he puts like these reagents like PDOAC2, PTO2, CaCO3, associate that with Lindlar's catalyst, which stops at the cis alkene. Right. Yeah. Now the last reaction here is called dissolving metal reduction, and you do need to know the mechanism for that. And this is the one with the radicals. Like this is one of the reactions with the radicals. Do you guys want to go over this mechanism, or you guys have it in your note card, and then we could move on to the next reaction? I could go over this mechanism and explain like step by step what's going on here on the dissolving metal reduction, or move on to number 7.
Is this the one with the radical?
Yeah, this is one of the reactions with the radical. Yeah, let me just show it to you really quick. Yeah, right here. Okay, so I'm just gonna use a simple alkyne so that I could draw the mechanism easily. Let's say asymmetrical internal alkyne, like that. If you see Na NH3 liquid, this Na here is not positively charged. We're used to seeing Na with a positive charge, but this is not positively charged. It's neutral with a radical. It's a metal with ammonia liquid. That's our solvent, right? We know that this is going to create our trans alkene. So let's start there. That's our product, right? If you want to keep track of the atoms, you could say this is 1, 2, 3, 4, 5. That's 1, 2, 3, 4, 5. The triple bond between 3 and 4 became a trans alkene at 3 and 4, right there. Now, let's do the mechanism. And I'm going to separate this into 4 different steps to have a pattern here, right? The first one is going to be radical addition. Second step is going to be acid base. And we repeat that one more time. Third step, radical addition. Fourth step, acid base. Okay, and we're going to see that here. So, mech. This sodium here has 1 radical, 1 lone electron, which can move and attack one of the carbons of the alkyne. Doesn't matter. They're both equally substituted. When that happens, one of the pi bonds, those 2 electrons are going to go to the other carbon, creating a negative charge on the other side. Which gives us this intermediate here, right? This 1 radical here came from that sodium radical. This pair of electrons here, those 2 electrons came from the 2 electrons of that bond that moved onto the other carbon right there. And I changed the geometry here. Before it was linear, but because it's now a double bond, it's now like in this 120-degree angle shape. Right? Now, the next step, acid base. We want to get rid of that negative charge, so we bring in an acid. And our most acidic source is the NH3. Right? This is NH3 right here. That's going to be our proton source. We're going to grab that hydrogen and kick out NH2 minus to give us this neutral alkene radical here. Right? This carbon is no longer negatively charged because it has a hydrogen now, which came from that NH3 right there. Right? Now we repeat. We do another radical addition, bring in another sodium radical, and give that carbon there with the radical another pair of electrons to make it into a negative charge, carb anion. Once we have this carb anion, we do another acid base to give us our final answer. Right. And the reason why we stop at the trans alkene instead of the cis alkene is because when this sodium radical here comes in to attack that carbon and this pair of electrons goes on the other carbon, right? These carbons here are flat and planar. These sp carbons here are flat and planar. So it could have formed that intermediate, or it could have formed this intermediate here, right? Because it could have like gone in either direction. But the trans alkene is more stable than the cis alkene due to steric hindrance. So that's one of the common factors in OChem that you can use to explain. Like steric hindrance is a big factor and resonance is a big factor. Like if you guys get stuck, an explanation problem for helix class especially, if you say like something with resonance or steric hindrance, then you'll most likely get some points for that, right? Because a lot of OChem comes down to resonance, steric hindrance, yeah, a lot of things break down to those foundational concepts. P orbitals push away from each other. So if there's a double bond here, which there is, the p orbitals here are directly overlapping, right? So they want to be parallel to each other. They want to be parallel to each other. But when you think of this lone electron here, trying to add onto this carbon right here to give that carbon a radical, right? That's gonna like break the octet rule for this carbon if we don't do anything else, right? Like let's just say we try to put that arrow right there. It's one single hook arrow to give that one carbon 1 electron. That means that this carbon here is gonna have 2, 4, 6, 8, 9 electrons. That's not good, right? That breaks the octet rule. So to conserve the octet rule, or no, we're not really conserving the octet rule here because we're breaking this bond and giving this carbon a negative charge. This carbon here still has 1 hydrogen. Oh, no. Wait. Yeah, this carbon here had no hydrogens to begin with. So this has 2, 4, 6, 7 electrons, right? So that means this radical here is still on a p orbital, but it has 1 electron. It can accept 1 more electron, which it does in the mechanism at some point, right? So the p orbitals pushing away from each other would happen from this arrow, I would say, right? Because this bond here is coming from a direct parallel p orbital overlap. And I guess you could say those p orbitals are gonna break away, push away from each other when those 2 electrons go onto that carbon. That's when the p orbitals would push away from each other. That's when the p orbitals would break and no longer be parallel from each other, right? Mhm. Did that make sense, Alicia?
Yeah, yeah, I think it did. You said when it goes on to the SP goes
Yes.
on to.
Yeah, when this bond breaks, that's when the p orbitals break apart from each other.
Okay, that
Yeah.
makes sense. Thank you.
Right. Yeah. Okay, so that's dissolving metal reduction, which is going to be one of the mechanisms you need to know for the next midterm. Let's move on to the next one, number 7. Okay. 7, 8, and 9, they're all hydrohalogenation, but the difference between them is that 7 is a terminal alkyne, 8 is an asymmetrical internal alkyne, and 9 is... Oh, no. 8 is a symmetrical internal alkyne, right? These two arguments here are symmetrical. They're the same. So that's a symmetrical internal alkyne, and then 9 is an asymmetrical internal alkyne. And that makes a big difference on how many products you produce, like Elisa said at the beginning of the session. So let's do that. Let's do number 7. Do you guys remember what happens when we have this alkene, simple alkene, let's say, and react it with HBr? Like, what product gets formed here? And what does the mechanism look like? Okay, let's do an alkene reaction review. Hydrohalogenation.
Does
Addition.
the alkene attack the or like grab the hydrogen, and then
Mm-hmm.
the bond between hydrogen and bromine break,
Mm-hmm.
and then I think the bromine comes in
Mm-hmm.
again and attacks.
This carbocation, right? But
Yes.
I give you guys a simple example here. What step do you also have to watch out for? You look out for once you get this carbocation intermediate before the bromine minus
Hydride
attacks.
shift?
Hydride shift or methyl shift. That's correct. In this case, we don't have to worry about that, right? But if it was something like that, then you would do a hydride shift, and then the bromine minus attacks the carbocation, right? That's good. Nice. And then we added bromine right there. Markov-Markov addition. Okay, let's do the same thing here, right? Alkynes are just like alkenes, but we do the reaction one more time. So we're gonna attack that hydrogen, kick out the halogen, and create this positive charge here at the more position, but this is not a single bond, right? Because we used one of the pi bonds here. If I highlight that in yellow, that's this bond right here in yellow, grabbing this hydrogen right here, which is, let's say, in blue. That's this blue hydrogen right there, right? So we just get rid of one bond. There's still a double bond right there. Now, we don't do hydride shift here because the positive charge is on this double bond, and we don't do hydride shift if the positive charge is on the double bond. The CO minus just attacks that carbocation right away to attach a chlorine right there. Right. Now, we don't stop here. We will stop here if this is one equivalent, but even if you just see HCl, assume excess amount, right, for Helix's test. It's only when you see explicitly written out 1 EQ of HCl, this is when you stop here. If you don't see anything or excess or 2 equivalent, then we could do it again because we have an alkene, and this is the regular alkene reaction, right? Where we're gonna put a positive charge right there, where this positive charge is very stabilized by the chlorine's pair of electrons, which could do resonance like that, right? So then another chlorine ion is gonna attack chloride ion, is gonna attack that carbocation to give us this dihalide. But it's not a vicinal dihalide because they're on the same carbon. They're not adjacent to each other. Same carbon dihalide, or dihalide, right? Like that. And this is a terminal alkyne reactant, and we stop here. One product, Markov-Markov addition, because there is a clear more sub position here, which is this carbon right there. Okay. So this was basically the alkene reaction 2 times. Now let's do number 8. Okay. So for number 8, it's gonna be the same mechanism. Let's protonate the alkyne and give a positive charge on the more subcarbon. In this case, since it's an internal alkyne, both carbons are equally substituted. There's no more subcarbon, there's no less subcarbon. So it doesn't matter where we put the positive charge here. Let's put the positive charge on top. And Br minus attacks. Get this intermediate. we have excess amount, we have a second equivalent somewhere, bring that in, protonate the alkene, create this carbocation intermediate. Underneath the bromine, Br minus comes in, attacks the carbocation, give us this final product here. Right, now you might ask, why do we not get this product here where we attach the bromine on the other carbon of the alkyne? Because they are both equally substituted. You can, right? But they are identical structures, right? It's just flipped or rotated around, because if you track this carbon here with the dihalide, the two halogens, they have the same chemical environment. This carbon here with the two bromines is attached to, let's say, this sec-butyl group, right? This carbon here is also missing this carbon right here. Boom. It's also attached to a sec-butyl group right here. Right, and then this carbon here is also attached to this, let's say, CH2 isopropyl, which is, what's going on here? Okay, let's number it. Let's say this is 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7. Missing a carbon. So that's why when I do these problems, I like numbering my molecule, because I would not that's how I would avoid like losing a carbon. I lost a carbon here when I first drew out that product. This here, miso, this would not be miso because there's no chiral, well, there is a chiral center, but there's no plane of symmetry present here. No plane of symmetry. So this would not be miso. Right? No plane of symmetry. 1, 2, 3, 4, 5. Miso, we need like at least 2 chiral centers, most likely 2 chiral centers, and a plane of symmetry. Right? There are 2 chiral centers here, but there's no plane of symmetry here. 6, 7, 8. Okay, that's good. Did I draw the other product out correctly? Let's see. 1, 2, 3, 4, 5, 6, 7, 8. Okay, so the 2 bromines here could have been on carbon 4 or carbon 5, right? Carbon 4 or carbon 5. But we only draw one product here because they are equally like the same. They're identical. Like this purple carbon here is attached to this sec-butyl, sec-butyl. This bulky group is the same bulky group as this bulky group right there. So because they're the same, it's just flipped or rotated. We only draw out one product for predicted product. Right. And this is not miso because there's no plane of symmetry here. No plane of symmetry in this molecule. Right. Okay. Number 9. I'm just gonna draw out the 2 different products here because this time we have an asymmetrical internal alkyne. The mechanism is the same, but if I number it 1, 2, 3, 4, 5 coming off of the ring, my 2 chlorines could have been on carbons 2 or 3, right? 1, 2, 3, 4, 5. Let's say this is 1, 2, 3, 4, 5. Added extra carbon. So that's why I like numbering these, right? So on the test, I would recommend numbering for sure. So you don't add a carbon or lose a carbon. Carbon 4 has 2 methyl groups like that. And then we could put 2 chlorines on carbon 2. Or our other unique product could be our 2 chlorines on carbon 3 because they're actually different this time. Right? They have different chemical environments. These green carbons here. So an asymmetrical internal alkyne, like this one, gives you 2 different products equally. 50-50. So you would have to put both products in predicted product if this was an asymmetrical internal alkyne. In the symmetrical internal alkyne case, like this one, we only get 1 unique product. In the terminal alkyne, we only get 1 unique product. But the asymmetrical internal alkyne with this hydrohalogenation reagent gets 2 different unique products, like that. Because the chlorines could have added on that carbon or this carbon, equally substituted. And they're different chemical environment. Okay, Any questions on this type of reaction? Hydrohalogenation of alkyne. 3 different types of alkyne: terminal, asymmetrical internal, symmetrical internal. How many reactions are there left? There's halogenation, mercury acid, that's 2, 3, 4. Okay. 4 different alkyne reactions left here. Yeah, that's good. Okay. I will have another midterm 2 review session for Helix class next week on Tuesday night, 9 to 11 p.m. Yeah. I'll create a similar practice one soon by then. Okay. Yeah. So yeah, that's good. Okay.
Thank you so much.
Yeah, of course. I'll see you guys then.
Bye bye.
Bye bye. Yeah.
I was wondering if you could send me the problems we didn't get to, because like I am at the point where I'm like trying to understand mechanisms now. Like I have them all down on flashcards.
Mm-hmm.
Do you want to
Yeah.
see all my flashcards? There's so
Yeah.
many.
I want to see.
Okay.
Let's see.
Here.
Oh my
Wait, I have
gosh.
so many. These are like only some of them. Like I have okay, this is the back. Whoops.
Yeah.
But there's so like here, I'll show you how thick they are. Look how thick they are.
Oh my god. Did you do these
then-
last midterm too, or did you just start doing these flashcards now?
No, I've been working on it. This is from the other midterm.
Oh my god. That's
See?
so good.
So I know I'm starting to run out of flashcards. These are like the big ones. Then I have these ones. And then I have the big ones too.
Oh my
and
god.
then I also saved my cheat sheet from last quarter.
Oh wow.
Which I didn't even get to finish, which is so sad because like I could have used the look at all that space.
Yeah, you wanted an A flashcard, right? For
Yeah.
Oh my god, wow.
I know, but like since we're like going back over some of the mechanisms from like A, like I'm looking at it every now and then. So.
Every now and then, yeah, like epoxide ring
Yeah.
opening and the Grignard reactions. Oh my gosh. Did you also include that for your midterm OneNote card, flashcard as well?
I'm gonna be honest, it wasn't as like I guess I did use it, but I kind of like knew the mechanism, so like I thought the predictive product was easy, which I think it was, but I was like I was doing that exam off of 1 hour
Oh shoot.
of sleep.
An hour of sleep. I remember. I remember.
Yeah, and I looked at some of my answers, and then I was like, yeah, I did not get sleep. Like and the thing was, I showed up to the exam feeling a little too confident predicting the products.
Oh
and I'm like,
And then you saw afterwards, and then, you knew it before, but then you're like, what are you doing there?
No, the thing is, like, I thought I knew it during the exam, so but I don't know. I was probably like, I don't know if there was a word to say high, but like sleepy high.
Yeah.
Like I would say that.
Oh my god.
I will not do that. That's why I'm kind of like doing everything this week. So I don't. That does not. That does not
happen again. And do you have any other exams next week, or is it just the 118B midterm?
It's just that one. I'm gonna be honest. Bio, I focused so much over the weekend. You know, cause I had bio and then OChem, so I was grinding bio. But the thing was, like, the average was 60.
Average, yes, for both sections I heard for the midterm one.
For bio.
Oh, for bio. What,
for
really?
bio, I know, and normally I heard the bio's like average is 80 in
Yeah.
other classes. So like my professors, they gave us a midterm that was like the same practice midterm as everyone else, but the way that they were grading was very specific. Like they wanted to hear actual terms, like if you were a grad student basically. That's what my friend was
Oh
saying.
no.
Like the responses that they expected were like maybe
Uh-huh.
how grad students would respond to them.
Yeah,
So
like
I didn't bring up Rubisco or chemistry. I don't
oh
know.
no.
Like
Hey, which
I was
bio was this?
very
Like Biz 2
B.
B? Oh my god.
Yeah, so I was like kind of crashing out because I actually
Yeah.
spent so much time.
Time on
I
it
just I
and
didn't know how specific because I thought
uh-huh.
the midterm would be like what's it called? Cumulative or like
Cumulative.
same as like what I would expect on the actual midterm they gave.
Yeah.
So I kind of got a really bad score. But
Oh
like I
no.
I understood all the material. I just wasn't like
Like specific, detailed enough. You didn't
yeah,
expect that. That's
I
weird.
didn't. So like I'm
And the ones that they gave you, that was from previous quarter. Like, did you notice a difference in detail as well for the key and like this quarter's
That's the
midterm?
thing, like this practice midterm was like a midterm that like probably all like professors use.
Mm.
So it's like the ones that it's not even like ones that they would typically
Oh,
create. So the answer keys and everything were very like broad. It was like just the
yeah.
most general like details or ideas.
Mm-hmm.
So I was like very much humbled.
Oh.
I was so torn.
Oh my
I was
gosh.
yeah,
Wait, let
but
me
at
see
least
if
I
I
know
have
what to
my
expect.
Biz 2B folder because I have like photos of all my
Yeah.
different classes at UC Davis, and let me see if I can share that to you. And let me see that might help. It might not help. Who's your professor?
Yeah. Uh. Ooh. It's some like older lady and this one
Yeah,
guy. I forgot.
it's okay. It's
Let
okay.
me
I
just
also
double
had two
check.
professors. I
Yeah.
remember Furrow was one of them, and Keen. I think yeah, Furrow and Keen.
Yeah, I
Furrow and
heard they
Keen.
were there for last quarter, but I didn't. I wanted to, but I was kind of scared to take 3 stems. And so
Oh.
like yeah, so now like this is my very first quarter taking up 3 stems, and like
Uh-huh.
I don't know. It's oh I have I think Robert.
Right.
Robert Randolph
Oh,
and like some other one.
yeah.
She's like an older lady, but
Uh-huh.
um yeah, they're very much like very specific on like the responses that they asked for. I actually have to like base my studying
Mm-hmm.
on the learning
Oh
objectives
yes, yes.
because I
Learning
think
just.
that's how they do it. I kind of that's kind of
Mhm.
what I noticed after that the if you study the actual learning objectives, like the goals, even
Mhm.
though like it's kind of broad, I just have that's how specific or like that's how much I have to be confident in like the
Mhm.
material.
Yeah, I know. It's very detailed. I do have like learning objectives files here. I see.
Hmm.
So let me share it to you on this drive with the pre-labs, all the pre-labs as well.
Oh my
Uh,
gosh, right? Stop.
just let me know what
Oh
classes
my
you take, because
gosh.
I will most likely have
Yeah.
folders for it. So just
Oh
let me
my
know on
gosh.
Discord, and I'll share it to you. Can you send me
Yeah.
the email that you want me to send it to on
Yes,
Discord?
please. Bro, you might be
Yeah.
the reason why I'm able to survive this quarter. There might be hope.
What other classes are you taking this quarter? Biz 2B, Chem 118B.
I'm finishing up my 17th C or like 17th
Oh
series,
yeah,
so
yeah,
it's
yeah,
with
yeah.
C. So
Mm-hmm.
that one's kind of easy.
Mm-hmm.
It's just I've been focusing on both of those two classes, OChem and
And bio.
bio. Yeah,
Yes,
because
I
bio is
know.
new to me. I haven't done bio since ninth grade of high
Ninth grade high
school.
school. Oh shoot,
Yeah,
that's like 5 years
so
ago for you. Oh yeah, 5 years ago.
yeah, so like it's yeah, I am a bit rusty, and plus we didn't learn that much. But
Uh,
I mean, I am interested in it. It's just
yeah.
that
You.
midterm took yeah, the grading took me by surprise.
Yeah, humbled you,
It
lazy.
really did.
Oh
But it's
no.
okay.
Yeah.
I mean like I'm trying to see like the positive side of all of this. It's
Mm-hmm.
just like I'm that was my goal to like really figure out my study habits.
Yeah.
So like I guess that kind of, you know, sadly this is the way I have to
Sadly.
learn.
I know. Like, how did you study for the first midterm? Did you do flashcards, Quizlets? Did
Yes,
you
I created that's a thing for bio. Like
Yeah.
I don't know people who make flashcards for bio, but from the experiences of many, I haven't heard I haven't heard they were like, "Oh yeah, I just go over my notes. That's
Oh my gosh,
it.
yeah. It's kind of hard studying over your notes too, because
Uh,
like, how do you test yourself like that? Because flashcards, you can test
yeah.
yourself. But what I recommend is that try like teaching it to like yourself in detail
Yeah.
from the beginning, and make it organized notes like because it's all over the place, all the material. So try to organize them into like different categories of like content.
Yeah, I know. I know I'm like we're going over like natural selection, genes, genotypes,
Mm,
phenotypes, and it's like it's getting to the very much like specific stuff. So I have to like
mm.
really start studying on that stuff. So like
Mhm.
I'm trying to keep a balance, but I really want to pass OChem because
Yeah.
I'll admit my exam was like
Mhm.
kind of where average was.
Mm.
So I'm not
Yeah.
proud of it,
Mhm.
but
How many
yeah.
hours of sleep did you get the night before?
Literally 1 hour.
1 hour
That's
too?
what I'm saying. Oh wait, for bio?
No,
I
no,
think
no, no, no.
bio.
For
Oh, for
the
OChem.
118 outcome brand, yeah.
Yeah, literally just one
1 hour.
hour.
Just like the 118 A final, like that, 1 hour.
Oh, for 1 8. Yeah, I actually pulled an all-nighter for the one like
Oh,
the
so you
final.
got no sleep for the 118 A final, like.
Yeah, I mean, like the way I thought of it was like I know I have time to like really like
Mm-hmm.
pass, so like I
Yeah.
I take advantage of that because I
Yeah.
if I went to sleep knowing that I'm not confident in
Uh-huh. Uh-huh.
any of my answers or like just in
Yeah.
certain parts,
Mm-hmm.
like I feel like I didn't try hard enough.
Kind of,
So
yeah, because like, you didn't give it as all. I feel like I do the same as well. Like when I'm not confident in anything, like I tend to like sleep very late or pull all nighters too. That's
yeah,
me too. Like,
like I want to feel like I tried my best,
yes, and that's why you're starting
but
early now, like so you could
yeah.
avoid that next week for the next midterm.
That's what
Yeah.
I've always wanted to do. It's just like there's like so much material like in different subjects, like and it's like at different paces. So
I know. Yes. But I did send you the alkyne reactions and mechanisms, so you could try that out.
okay, yay.
Um.
Thank you, Brian.
Yeah. Of course, Alicia.
Oh my gosh, thank you.
Yeah. Now you
Yeah,
got you
I'll
got
keep
other
you
resources for
updated.
bio and OChem. So like,
Yes.
yes, that's good.
Yeah, and the labs, the pre-labs, let me say, they some of them are just
Uh,
I don't know, the questions are a little like odd. Like
oh, the pre-lab questions. Wait, let me see the pre-lab
yes. Like
one
some of
here
them
really
are
quick.
like they ask the question in a completely different way. Like they ask you, I think one of them was like interpret the graph of a logistic and
Uh-huh.
an exponential. And so
Uh-huh.
I drew they're like, "Oh, draw out the graph that this description of the population
Uh,
is to be, right? Without any
yeah.
factors influencing it." So I said
Uh-huh.
exponential. And then literally the next page was, "Does this match with logistic?" Like the graph that you drew previously, I'm like, no. Like it's like they asked the question in a different way. It's
But
like the same
yeah,
thing though.
same thing but different way.
So I'm like going insane because like I am
Uh,
trying to understand it because I know this will be important for
mm,
the lab practical.
practical,
Lab,
yes. There's
yeah,
different stations you have to like rotate
yes,
around. Well, I
yeah,
do like had it. I did had it online, so it was like easier for me. I had
yeah.
my notes open and everything. But yours,
Mm-hmm.
like closed note, no open note, no flashcards, no cheat sheet or anything, right? So
Yeah,
you had it. You have it harder. So you
I
actually have to
know, but
understand.
I mean, like, I feel like that's just like what I really want to get out of these courses. It's just,
Yes,
the system, like, it
I
makes it
know.
really hard.
I know. I
It makes it
know.
hard to like,
Unfortunately.
yeah, pass, but also want to learn.
I know. Like you actually want to understand the material, but like
Yeah.
it's like the time and you just like resort to memorization, unfortunately, especially before the exam, like right before the exam.
Let me tell you, like, and from the beginning of bio, I was actually like handwriting my notes,
Uh-huh.
and in like I would like pre-handwrite it, but the
Hmm.
thing is, like, now at the pace of like bio
Yeah.
alone, I'm only like annotating slides now. So
Oh,
I don't know if that's a good or bad thing, but I feel like I'm spending less time trying to just like write everything down.
oh,
I
did you
think
write
just
everything
like
down by scratch without the slides? Like,
yeah,
wait, wait,
yeah.
wait, what?
I mean, I think that's kind of bad, but like
What?
I don't I know, and I kind of started seeing like I don't know why I started observing, seeing how people like wrote their notes during
Notes, yeah,
class, and they always had the slides up. And I'm like,
yes.
why? I'm like, they're crazy.
No, 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 you're crazy, Lisa. You're crazy for not doing that. Yeah, like
I
writing outfit,
know.
you just write down whatever is not on the slides because whatever's
Yeah,
on the slides, you just read
literally.
over that. I know. Oh my
I know.
God.
I'm kind of embarrassed because like, here, let me turn on my
Yeah, yeah.
computer. Look,
Uh-huh.
like this is like all
And your
like
notes are
the
so neat too.
actual.
All your handwriting too. Like I don't
I
know how
mean,
you do that. Like during
I
lecture,
mean,
how do you catch up?
well, for the objectives, I kind of just like type those up, and then I
Uh-huh.
let me tell you, like for calc, it's like a little bit messier.
Mm-hmm.
I don't know if you would think it's messy, but this is like on
Yeah,
the spot.
yeah. I want to
Here,
see your
let me
math
show
work.
you.
I haven't touched
Here.
math since freshman year, first year of college.
Really?
Yes.
Yeah, this is like all calc.
Oh my
And like
God.
this is like actually on the spot too, so I don't
Mm.
rewrite either. I don't have the time to rewrite.
Yeah. Oh, yeah. Oh my God, so organized. Like all your notes.
I
That's-
try to be, but I
Yeah,
mean, I mean,
that's
I
so
think
good.
over time after like using an iPad, I've like kind of organized it in a way where I can like organize it at the same
Hmm.
time.
Yeah.
So yeah, it's
Yeah.
gotten better from like the first set of my notes from like first quarter. Yeah.
Yeah, that's so good. Oh my God. When did you switch over to like annotating on the lecture slides?
Literally just like last week.
Oh, so like ever since you had an iPad, you just been writing like the notes from scratch
Yes.
without the lecture slides? That's crazy, Alicia.
Yeah,
That's
and I
crazy.
mean, I
Oh
kind of
my
feel bad for
gosh.
myself that I was that slow to like realize that,
I
but
know.
I think that's the move because like I can actually like some
Save a lot of
how
time.
I thought of it was like I would watch the lecture again and then rewrite my
Uh-huh.
notes.
Yeah, yeah.
But I think if I have like the slides already down, then I could just
Mm-hmm.
annotate and also listen at the same time.
Mm-hmm. Yeah, and that's good too because like if you do rewatch it, that's more time, less time studying like yourself and like actually trying to understand it, you know? Like you could
Yeah.
have it on the spot during live lecture as well. Like, do you go to all in-person lecture slides, live lectures?
Yes, yes,
That's good.
I
That's good.
do.
Yeah, 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 that's good.
I tried to, but then again, like what I always struggled with was like writing notes, but
Hmm.
also understanding it at the same time.
Yeah, yeah, I know, I
So,
know.
like
That's
downloading the
hard.
slides kind of help minimize the amount of writing
Mm-hmm.
to really focus on what they're saying.
Yes, yes. That's crazy, Elisa.
Dang.
Because before you were just focusing on like writing and then you're not even like understanding anything. You just like copy pasting everything. No,
Yeah.
Lisa, no,
Let's keep that a secret between us.
Okay, okay, okay.
Yeah, I don't think a lot of people know that, but
Yeah.
I mean, I think that's different for calculus because calculus you actually need to write, but
Oh yes,
like as
yes.
far as like anything else, I think
Hmm.
annotating is like the
Yeah,
that's the move.
I know. You gotta show me how you study too, so I can see what you're doing and give you
Yeah,
some tips.
I'll keep you updated on like,
Yeah.
if I'm surviving or not, but I
Yes,
mean,
yes.
you've been a big help.
I saw
So,
your forest app like thing today. It was like 5 hours,
oh
6 hours.
yes, I got half of what you had yesterday.
Oh my gosh.
Yeah, I think it was like you had like 4 hours and then I only
Uh-huh.
got like 2.5.
Oh my
So
God. That's good still. Yeah. Those four
yeah.
hours was like the all-nighter hours I had, like, because I had 3 exams today. And then I was
Oh, okay.
that's between those 4 hours, like, just trying to focus
Yeah. I know, I
on
noticed
for
like,
my
okay,
exams.
Brian's on the move. I was like, I think I saw you from like from the beginning of the day and I was like
Yeah, yeah.
0. And then like
Uh,
later on and towards when I was gonna
uh-huh.
start studying, I saw you had like 4 hours
Yeah, yeah.
already. I'm like, wow.
Yes. That's so good.
Okay, but that does make sense. I was like, okay, no wonder. Because then you're
Yeah.
saying like you had all your midterms and stuff.
Yeah,
So
yeah, I know, I know.
yeah,
I'm gonna have to
but
do
you
it
still have
again.
one more too. So I'll probably see more trees.
Yes, yes, you will. You definitely will.
Yeah.
uh,
Okay.
yeah.
Thank you for the little chat.
Yeah, of course, of course.
That was
Alicia.
okay. Thanks,
Yeah.
Brian.
Yeah, no problem, Alicia. Good night.
Thank you. Good night. See you tomorrow.
See you tomorrow.